The personal assistants, smart thermometers, smart lights, smart appliances, gadgets, and other objects have transformed our lives and many things into a new level. An operating system can synergistically provide capability for those devices to handle complex tasks, as well as a framework and an ecosystem for us to focus on the creation of such smart devices with the software applications in many industry verticals. This course talks about the applications from the OS-based perspective. I'll walk you through all the essential building blocks, and I'll also show you how things are done in different examples. I'm Ryan Hu, and I'm an engineer, researcher, and professor in the field of IoT. I'm really excited to share all of this with you, so let's get started. Operating system concepts. If you need to learn about these concepts, you can check out my course, IoT Foundations, Operating System Fundamentals. To do the exercises in some demos is also helpful if you know C programming language or a similar one, but it's fine if you don't. You can follow along to watch them. In a few videos, I'll reference some hardware platforms and software tools as examples. It is not necessary to purchase any hardware or download any software to follow along with the course. And take our voice commands to control other devices connected. How the smart devices can talk to each other, or how to deal with the data we've collected over time. On each device, there's most likely an operating system application program up and running, taking care of multiple tasks such as handling sensors, transferring and processing data, safeguarding the data and software, and taking user controls. Using an OS to develop your IoT device software is usually an important step toward building your exciting IoT products for many vertical applications. In general, developing your IoT systems on top of an OS brings an ecosystem that you can utilize for your products. An OS essentially provides a development framework that you can build your applications more easily. More specifically, let's look at the benefits based on the generic system architecture of an OS. An operating system may have many forms, but things get clear if we keep in mind that it usually has a kernel that does the fundamental heavy duties for your software, such as managing tasks and memory, providing interfaces for hardware components, or managing clocks. Then around that, an OS may add some built-in features in the form of utility functions and software libraries. Some examples include crypto libraries for security, cloud connectors for interacting with various cloud endpoints, networking stacks for data transfers, security and software management, as well as add-on device drivers that can make our software manipulate many peripherals such as sensors and actuators. As for the application software built with an OS, there are some key high-level characteristics we care about. The first is the robustness. Basically, we expect our IoT device to run stably for as long as possible. It is true that it's related to many factors, but in general, the robustness of our OS-based applications can be enhanced by the debugging features that may be provided by an OS. This is especially important for the real-time applications using a real-time operating systems, where the timing sequence of the task execution needs to be carefully considered in the design and the development phase. The debugging, testing, and code analysis are related considerations in order to develop robust OS-based applications. Security. For an OS application, it involves the software security and the network security where the platform is trustworthy, the software running on top of it should be secure, as well as the data stored on the device and the transfer through the networks is secure. Modularity and extensibility are something that we can make our application flexible enough to add or remove features. In the ideal case, our application features are developed on a modular basis and any issues happen to one software module and the runtime won't affect the others. If your IoT solution requires a scalable deployment in geographically distributed areas, applications beyond the kernel, every application has a set of functional components as building blocks, where some common ones can be broken down into the following topics. These components in general can equip an IoT solution with some unique attributes that can synergistically make our solution solid and innovative. Let's briefly look at them one by one. A key attribute of an IoT application is its sensing and actuation capabilities. Since the general paradigm of many IoT devices includes collecting and utilizing data, an IoT application can be considered as data-centric, whereas the data may be referred to little data or big data from one or more IoT devices. This topic is therefore important to many applications, especially for the IoT solutions that rely on data for value creation. IoT devices are mostly equipped with one or more connectivity options, upon which data transmission is a key task involved in IoT applications. A data transmission process on these devices via various underlying communication networks makes message exchange possible between devices and users across a short to long geographical distance. Interoperability is key to today's IoT applications. We'll discuss how an end-to-end interoperability is done with a typical software frameworks. Cloud and edge computing means a lot to an IoT system. If it's viewed as a global IT infrastructure connected by the internet, cloud and edge computing enables the new features into connected IoT solutions across industry verticals. Device management is key to your IoT solution, involving the deployment of networks of IoT or machine-to-machine devices. We'll overview and discuss some key features of the device management. Security is a standard feature that needs to be added to many IoT systems. We'll review the levels of security from device level to application level. Last but not least, artificial intelligence and machine learning. This topic is where an IoT solution can benefit from the intelligence added to the board and to the networked IoT system. We'll talk about the intelligence that can be enabled in your IoT applications, which have been gaining intensive how an OS-based application is done. Usually, it's part of the software development process, and there are several models that can be used in such process. Here, let's follow the typical waterfall development model for the software development, and assume that we have completed the product requirements and the design phases, so we can focus on the implementation phase, which usually involves some testing or unit testing efforts on the software we develop. Suppose we have selected an OS running on your target IoT device platform, where an OS can be chosen among the embedded OSs or general-purpose OSs. First, you'll need to set up the development environment on your host computer, such as a PC. The environment can allow you to develop the software programs for the target platform, including the hardware and OS. If your target platform is similar to your host, you can just set up that on your host. If not, you'll need to set up a cross-platform environment on your host. For example, if you use your PC running a Windows OS as the host computer to develop the program for the Raspberry Pi running a Linux OS, this needs a cross-platform software development environment where we need to basically make sure the Linux cross-platform development tools are set up on your host. A development environment typically includes the compiler and debugger tools, as well as an IDE or a source code editor that facilitates your software development. You may need an SDK containing the OS kernel with the drivers and the software libraries. Depending on your needs, sometimes the SDK may contain everything you need to start with, but sometimes you'll have to add things manually. These things include software libraries and drivers that are well supported by manufacturers or user communities. If you work on a board without out-of-the-box support from an OS vendor, you'll need to port OS for a board. If a board has custom hardware modules, the porting is the necessary step to make sure the OS can boot and run on such custom board. You also need to make sure the required software components, such as the additional software libraries, for example, communication protocol stacks or cryptographic libraries, are in place and can work with the OS you've chosen. Once that's ready, we can start writing the software programs using the APIs from an OS and the software libraries. After you've written the programs, you'll need to do some testing and debugging with your target boards before moving to the next phase, your software development process. Speaking of the debugging alone, there are various ways of debugging software. If you connect your board to the host computer for debugging, you'll need to make sure there's a physical connection. as the bedrock of IoT. Sensing or actuation is considered as the basic capabilities of an IoT device. Sensors and actuators can be viewed as typical peripherals extended from your processors or microcontrollers, where they can be manipulated through the software interfaces. They can be physically connected to your IoT device through some standard hardware interfaces such as general-purpose input-output ports, buses, and the serial communication ports. In an OS, the software interface of making the sensors and actuators useful is through the sensor or actuator drivers. Most operating systems provide a hardware-independent layer that can allow us to manipulate peripherals. Let's look at some options to manipulate peripherals. First, we can simply do the polling approach to, for example, control the LEDs directly through the software interface whenever needed. For example, to control an LED, you can just assign a high or low voltage level to the GPIO pin of the microprocessor or microcontroller, connecting your LED in order to turn it on or off. Besides its simplicity, polling generally takes CPU time for waiting and polling the device. Alternatively, interrupts are considered as a general efficient way to interact with peripherals in real time. Instead of polling peripherals data from our program, the peripherals device will notify our program with interrupt events. In this case, an operating system usually provides the interrupt service routine to handle interrupt events for our applications. An interrupt event may come from the GPIO pins or any other ports. For example, a driver ported to an operating system can take care of the interrupt events of a physical sensor and service the interrupts. An image sensor using I2C bus as the physical connection to interface with our processor's I2C module can be configured to generate an interrupt signal through its I2C bus, received by the processor and finally handled by our OS-based application using the API functions. Another typical example is the reception of data through the network interface, say Ethernet or Wi-Fi. When a set of data packets was received by the network interface, an interrupt can be generated to let OS take care of it immediately, and then clear the buffer on the peripheral to let it receive more incoming data from the network. Some sensing devices need a bus interface to communicate with OS applications. For example, for an OS-based application with a CAN bus driver for the CAN controller module used, you can connect the CAN bus controller and the CAN bus transceiver to read many sensors in a vehicle, such as engine temperature, speed, steering, etc. Besides the GPIO and interrupts, an OS may also provide software interfaces for facilitating the direct memory access, called DMA. Including the biosensors that can be used in a broad range of applications, such as healthcare, medical analysis, bacteria detection, and environmental monitoring. Let's take a look at the popular fitness or activity trackers that can measure our heart rate and pulse oximetry. On your fitness tracker, there may be an electronic circuit board, like this one, while a biosensor can be used as a peripheral device connected to the serial communication port of your microcontroller. Let's look at the biosensor used by the fitness trackers here. There are many choices on the market. Here I just picked a integrated heart rate and pulse oximetry sensor named MAX30102. If we open the datasheet of this sensor, we can see some highlights from the system diagram on the first page, such as the hardware components including the I2C communication port used for communicating with our applications. First, let's check the principle of how the measurement is done. This sensor measures the SpO2 values, which give an estimation of the oxygen saturation level, as well as the heart rate values, both through the optical data read from the LED light, emitting to the skin of our body. Once the reading is done, we can use the communication interface I2C, meaning that we can use some wires for transmitting the serial data from this sensor to the minimalist microcontroller board. Now, let's see how to read the sensing values from your OS-based application. Inside the sensor, there are some registers and data buffers to hold the data for you, so we can read that through the I2C interface through the bus driver. If we read through the I2C interface, we can use the interrupt pin to generate interrupt events to be handled by the ISR. Once that's done, the buffer is cleared and the process can be repeated for new readings. The pure reading of data can be done on a simple application without an operating system, but you may want to handle some other tasks for that. Used actuators in robots, drones, and industrial systems. A motor can be virtually driven by any microcontrollers, while there are many kinds of them. Using pulse width modulation, PWM, is a common way for embedded systems to control the motors and other power systems. The PWM signals are nothing but a modulated signal, a series of on and off pulses with varying duty cycles. Let's see how it works. Suppose we have a connected robot with some wheels controlled by the few DC motors. The rotational speed of a DC motor is controlled by the magnetic fields, which can be controlled by the PWM signals. Each motor can simply make a wheel move forward or backward in various speeds. A combination of motors can make a robot do complex movements such as making left or right turns in different angles. Through the PWM signals to control the driver module of the motor, the on pulses indicate the high voltage applied to the DC motors, while the off pulses don't change the speed of DC motor. Thus, it is the on pulses that determine the speed of the motor at different times. There is an equation determining how the pulses can change the speed of a DC motor. But simply speaking, the longer the pulse is in on state, with good amplitude, the faster the motor will rotate. Now, the PWM signals can also be used to control your drums. An electronic speed control module is broadly used to control the brushless DC motors on a remote control drum. Therefore, if the PWM interface is available for a microcontroller or microprocessor, you can use the clocks to configure the frequencies of the PWM signals and output the signals to the GPIO pins. These PWM signals will finally make your drone fly. If you use a RTOS-based application on your drone, you can define the core components of many IoT applications. The data-centric IoT can be viewed based on the IoT system architecture, which are at high level split into three parts: local or field networks, network edges, and cloud. The sensing data is usually generated from a field network and transferred within its own network or between the field, edge, and cloud entities. Having that in mind, data management is about managing data from its generation, collection, fusion, to its processing, storage, and retrieval. Although the data management functions can be mapped to run on physical IoT devices, we may view it beyond these physical entities, as the data management entities may differ. For example, we may need some middleware pieces running on devices, edge, and cloud to accomplish some data management tasks. While what and how much data management functionality should be implemented is application-specific. For the simple applications, each sensor can just report the data to an endpoint, and users can access the data from the endpoint. Therefore, the data management functionalities such as generation, collection, storage, and retrieval are straightforward. For a complex application, data needs to be processed and fused out of data streams, coming from multiple sources. Let's look at what they mean in OS applications. First of all, data is generated by the data sources, such as sensors, and once it's generated, another entity should collect and process it. In general, a data source needs to be exposed to be used by another data subscriber. In this case, you might use some standardized protocol on top of your OS to provide such discovery interface. With the messaging protocol stack including an OS application, such as CoAP and MQTT, a data collection middleware residing in one device can obtain the messages published by the sensors and transfer them to another device or entity through a network. Since the data usually needs to be stored locally in a file or a database structure in the device, our application needs to use a file system or database driver for such purpose. For some time series data that needs to be acquired from multiple sensors, we also need to have a mechanism of ensuring the accuracy of the data. For example, some inaccurate timestamps associated with a set of data may make a fresh set of data be considered as a stale one. Thus, data with inaccurate timestamps should be adjusted or filter it out, or else it may introduce errors for later analysis. If we consider the case of a swarm of sensors on moving devices, such as micro-UAVs or drones, the data collection process gets more challenging as we need to deal with the possible connection disruptions between the drones and the timing synchronization. Data fusion is the technique of combining data from multiple sources and getting a better result than a single one. This can be implemented at different levels, such as at a single device, at the cluster head of a set of neighboring nodes, or at the gateway of a field IoT network. A typical example is the data fusion on a single device, which is equipped with multiple sensors such as accelerometer, gyroscope, inertial, and magnetic sensors. The data fusion algorithm on the device can determine the high-precision device orientation and the linear acceleration than the single accelerometer sensor can do. Another typical example is for industrial health monitoring of electrical motors. The accurate prediction on failure of any motor may not only depend on the data from one source, but multiple ones. Thus, if we have a gateway that collects all data, the data fusion algorithm can be done based on the data collected from sensors on multiple motors. After a data fusion job is done, we may need some processing or filtering of data before storing it to a local or remote data repository. Sometimes you may need basic processing tasks done at the edge where some data can be filtered out before transferring it to the data repository. Sometimes the data repository at the edge may only need to store a small amount of data after being processed out of the big. Aligned with the data management needs. To enable the data processing capability, we need some math or digital signal processing libraries. A basic function included in this library is fast Fourier transform, called FFT, which is a digital signal processing algorithm basically, used for calculating frequencies out of time series signals and has very broad applications, such as radio signal processing, audio data analysis, as shown here, which displays the frequencies of an audio sample when an airplane is taking off with the Gold Wave software, as well as machine maintenance and diagnostics, where we can use the FFT to easily spot the pattern or abnormality out of a large set of time series data. Here, let's see how to use a dedicated FFT-C library named FFTW to do a simple signal processing job. This library can work on many systems, although there might be some adjustments required to be done. In this demo, we'll generate a sample time series signal and calculate the frequencies contained in the signal with FFT. In reality, this signal may come from monitoring sensors on a machine, and we can check if the frequencies out of these sensing signals are normal or not. To see how to use the FFTW library, let's open the exercise file directory for this chapter, where you'll see a Visual Studio project where the FFT library is included and configured. So, you can easily compile it on Windows. For Linux or Mac users, you can compile it with the G++ as indicated in the README file. If you open the Visual Studio solution file, you'll see the main source file called fftexample.cpp. In the main function of this source file, we'll first define some data structures for storing the results and signals at lines 57 and 58. Then, we'll create a plan at line 60 and call the custom function we defined at line 42 to generate a test signal, which is a composite sine wave. After that, at the line 67, we execute FFT calculation based on the plan and get some results. At last, we print out the results together with the original raw signal to the screen. Now, let's build a project. Since we've configured to use a 32-bit version of FFTW library, we'll need to compile it for the x86 solution platform. Now, we can execute this program we just compiled. We can see that there are two sets of data printed out. One is for the original signal, and the other is for the frequencies contained in the signal calculated. Let's go back to the exercise files directory. The sample results have been provided to you and plotted with Excel. If you open the Excel file, we can see that the raw signal in blue and 2 frequencies contained in the signal. Assume these are what we expect you to see, so that if you get different frequencies other than these 2, it might need to use an essential network connectivity to do data transmissions over communication networks. To transfer data via communication networks, we'll need to have the hardware and the software. The hardware module is a network interface controller or a radio interface module. Nowadays, there are many system-on-chip solutions with memory and network interface controller chipset integrated into one chip. So, if you use a system-on-chip solution, our IoT board will require less external components than a non-system-on-chip solution. The software part includes the drivers and the software interfaces that are mostly supported by an OS, extended from its OS kernel. The support from the OS for the interfaces includes the thread-safe and standardized operations, such as using Socket API for network programming. An API of a network stack in the form of a software library such as Berkeley sockets usually provides API functions for common data transmission-related operations. If we consider our IoT device board running OS application as a node in the network, these operations include establishing and configuring a connection, sending and receiving data over this connection, as well as closing the connection established. It's possible that connections are not required for some communication mechanisms or make the data transmission happen over internet or IP-based communication networks. Briefly speaking, the TCP/IP stack lets us enable our OS-based applications to establish end-to-end connections with standards-based protocols, including, for example, IP version 6 or version 4, UDP, and TCP, as well as messaging protocols on top of them, such as CoAP and MQTT. If you start building applications from a bare metal OS kernel, you'll need to add support for a TCP/IP stack. For a general-purpose OS such as a Linux OS, we can add the support for TCP/IP stack when setting up the network support using the kernel configuration tool. But for embedded OS or RTOS, we may need to add such a support manually. There are quite a few free and open-source TCP/IP stacks that we can use, such as LWIP, which has been widely used and can be ported to use in various embedded OSs, commonly seen on consumer electronic devices. Similar to other network connectivity options, such as Ethernet and Wi-Fi, Bluetooth involves the hardware network interface, a Bluetooth chipset, and the software, including the firmware and the software driver that can be used for the OS applications. Bluetooth has been broadly used in connecting gadgets within a person's space, and the new version, Bluetooth 5, has brought that to the next level, such as the extended range and the speed. All these provide much flexibility for our IoT products with Bluetooth connectivity. For many IoT devices running as low-power sensors, Bluetooth Low Energy, referred as BLE, as part of the Bluetooth specifications, is a popular option used in many embedded systems requiring low power usage. Now, let's look at BLE. If you look at BLE from OSI reference model, it is now integrated into the architecture as other connectivity options, as we can provide end-to-end connections and send Bluetooth packets through the connection over the internet. We can use the IPv6 protocol over the Bluetooth connections right now, which simplifies the programming and integration efforts, especially for IoT devices supporting multi-standard protocols. A recommended way of using Bluetooth, including BLE, is using the SDK provided by the vendor of the Bluetooth chipset. Taking the NRF52 development kit from Nordic Semiconductor as an example, the support for 6LoWPAN over BLE is contained in the SDK package for that kit, where it supports some on-RF development boards out of the box. On the other hand, how to manage the data sending and receiving tasks is handled by an OS. For example, if we use FreeRTOS, we can define different tasks and assign that provides a wide area coverage for an IoT network. There are a few cellular technologies for IoT. GSM and LTE are typical examples of making your IoT devices connected through regular cellular networks. LTE-M and MB-IoT provide low-power wide-area cellular options, where their support from carriers has been growing at a global scale. Because of its wide network coverage, we can use this connectivity option for many applications, including smart home and smart city, such as smart environment, smart street lights, smart parking, and smart buildings, etc. Taking the smart street lights as an example, we can have an IoT device with cellular module as a controller to control the citywide streetlights. In this illustration, we can use the wireless links from several streetlights connected to the near cellular base station before allowing the lights to connect to the remote control center. In this example, we can see the wireless links from several streetlights connected to the near cellular base stations before allowing the lights to connect to the remote cloud service endpoints via internet. For each streetlight, suppose we have a controller IoT board, including an LTE modem connected to our main processor as a peripheral through the serial UART interface, which can send and receive wireless signals from its antenna. And the light is controlled through the relay module connected to the GPIO port. Our OS-based application needs to do some tasks here. For example, operating the modem with 80 commands, sending on or off signals to control the light, as well as interacting with a remote cloud endpoint through an end-to-end connection. IoT devices talk to each other and to interoperate with each other. This level of interoperability utilizes the underlying communication connections for data transmissions. Take our home as an example. We have connected devices such as smart appliances, TVs, music players, lights, locks, security cameras, garage controllers from different vendors. And they can all be controlled possibly by a central controller that can take your voice commands and control other devices wirelessly. All these are related to the interoperability between the applications. Let's take a further look at this in different OS-based applications from a networking perspective. Suppose you are in the living room right now and you want to turn off all smart lights in the room upstairs. On your end, you issue the voice control commands to a central controller at home. And that controller running an OS-based application will take your speech data as sound waves from its mic, translate them into the actual control messages, and then encapsulate them into data packets in order to send out to the transceiver module, which can finally convert the packets physically into wireless signals that get radiated at the tip of its antenna into the air. Suppose those signals can be successfully received by the smart lights antennas and the radio transceivers. Then, each light will send them up to the application layer and do the decapsulation operations of the packets and parse the packets into the actual control messages. After that, it may simply invoke the GPIO API to issue a signal to turn on or off the light through a relay module. At this point, both central controller and smart lights can interoperate with each other. And the general principle behind this is that both the controller and smart lights know how to send, receive, and understand each other's information. Or simply put, they follow a protocol for such information exchange process. In this case, any connected devices following a protocol or an operational framework can interoperate with each other. Many times, the interoperability we'll talk about on IoT devices happens at the application layer of the system, handled by our OS-based applications. This means the devices may use various radio interfaces, but they all follow an open or proprietary information exchange protocol, so applications between them can interoperate. for the low-power mesh networks on top of the IEEE 802.15.4 compliant radios. Thread can help us build a networking application focusing on the application features with little worry about underlying communication protocols or platforms it's built upon. Thread focuses on mesh networking between radio nodes, which can avoid single point of failure. In a typical local mesh network, there are different rows of different IoT devices, including end devices, which can be sensing devices, thread router that connects end devices, and thread leader, as well as border router interfacing the local network with external network. OpenThread is an open-source implementation of the Thread protocol, released under the permissive BSD 3-clause license. It is OS and platform agnostic, meaning that it can be integrated into any OS, including the general-purpose full-fledged OSs such as Linux, Mac OS, and Windows, as well as embedded OSs such as FreeRTOS and Riot. The current OpenThread release comes with the built-in platform support, including the drivers for Windows 10, POSIX systems, and IEEE 802.15.4 radio chips from some major semiconductor manufacturers. OpenThread can be used on flexible platforms through its support for system-on-chip and network coprocessor platform solutions. System-on-chip means the radio module is built on the same chip as processors and other modules, which are broadly used in many microcontroller-based embedded systems, while coprocessor platform means the processor and the radio module can be in separate chips. Typical examples of network coprocessor solutions include the use of our Linux or Windows host to control a separate external NCP device running OpenThread. As an example, let's look at how OpenThread works on Windows 10. OpenThread provides the NCP driver for Windows 10 to allow the Windows 10 host to operate external devices running OpenThread through the UART port, running the so-called spinal protocol. There are 3 driver files: OTAPI.dll, OTLWF.sys, and OTTMP.sys. The first file provides the API and the Windows user mode to control the OpenThread protocol, while the OTLWF.sys file is in the Windows kernel, and it provides the OpenThread logic. And the last file, OTTMP.sys, is responsible for communicating with the external NCP device shown at the bottom. The OTLWF.sys file can be in the full stack mode, while the full OpenThread stack for enabling device-to-device interconnectivity. The IoTivity project is sponsored by the Open Connectivity Foundation. IoTivity is in compliance with the OCF specifications. The way the IoTivity project is managed is similar to that of OpenThread, but IoTivity and OpenThread have some differences in markets and aspects. IoTivity currently has some out-of-the-box support for some platforms and operating systems, such as Ubuntu, Raspbian, Windows, iOS, Android, macOS, as well as embedded OS and RTOS ports, such as Riot OS, Kentucky OS, and Zephyr. IoTivity can make devices interoperate with each other at the application layer. Technically, it provides a middleware layer with interfaces for the common operations required by the device-to-device connectivity, such as resource modeling, resource discovery, messaging, cloud, and security. To see how it works with various operating systems, let's look at the 2 streams that IoTivity is released in. They are IoTivity and IoTivity Constrained. The IoTivity stream is for regular devices with ample compute power and resources, while the IoTivity Constrained stream is for small or resource-constrained devices. IoTivity is currently built on top of the IP-based communication network protocols, with the possible extensions to support multiple transports for non-IP or proprietary communication networks. In this sense, IoTivity can be considered transport and radio agnostic. The IoTivity release contains the essential protocol stacks for device-to-device communications, such as TCP/IP, UDP, CoAP, and HTTP. The IoTivity base sits on top of the protocol stacks as the middleware layer to provide common interfaces to the applications, such as controlling the smart lights, TVs, and appliances in your home. Now, the IoTivity constraint stream contains the reduced protocol stacks in order to make it small, efficient, and low power for small IoT devices. We can see that only the essential network protocols, such as CoAP, UDP, and IP, are included in this stream. To get started using the IoTivity in your OS-based application, we can download the releases for a target OS at the IoTivity website, or check its GitHub page. Our application running on IoT devices in field networks that may be across a long distance can handle any data transmitted via an end-to-end connection. This end-to-end connection is logical, and the data transferred through that connection may be physically transferred through the network and computing devices at the edge and the cloud. Therefore, we can do something between the two ends, and doing some computing at the network edge is one of them, where it can bring some new solutions to an IoT system. Edge computing basically means the computing at the edge of the network, from the IT infrastructure's perspective. The similar fog computing concept depicts such concept in a way that it has a shorter distance to the field IoT devices in the network hierarchy than the cloud. A typical edge device mainly does two things: data and control. It collects data from field devices, processes and optimizes it before transferring it out to another internal or external networks. For some networks generating a big amount of data from field devices, for example, an industrial network with sensors for monitoring a production line, edge computing can help with doing some computing jobs based on the monitoring data received, and reduce the network traffic and make it more responsive and real-time. An edge device also does some control over the incoming and outgoing network traffic. The edge computing enables standardized framework and management tools for getting these two things done easier and better than before. An edge computing solution can also make a set of distributed edge devices work together in the network fabric to do some optimization of network traffic. In this way, we may need to configure and manage these devices in virtual or physical networks individually or collaboratively with edge computing. In real-world scenarios, an edge computing solution to our IoT network can be done on edge routers and gateways, while these devices usually run an embedded Linux or a general purpose with edge computing on a typical edge device, a gateway. A gateway can interact with field IoT devices, process data, manage data, and interface with external networks. A gateway as an edge device can be deployed for multiple purposes. For example, it can be part of a smart meter to interact with external cloud endpoint to process and transmit the electric energy consumption data collected from your devices at home. It can also be equipped with some machine learning capabilities to autonomously make predictive decisions on the sensing data to tell us how to reduce the energy consumption. For some proprietary IoT systems, the internal and external networks can be deployed within the same domain of an organization, which can bring some security benefits such as preventing the IoT system from external attacks. Fundamentally, a gateway on the edge needs to flexibly meet the requirements for different scenarios, which should be met by the OS-based applications running on top of it. There are different ways to achieve this goal. One way is using a middleware platform for the gateway applications, where the software services can be developed and deployed on a modular basis. Let's look at the Eclipse Cura project, which provides Java-based software framework and a middleware platform for building and running edge computing applications for gateways. It defines a standard way of processing data between edge and the devices with management tools. Since it's built on top of Java Virtual Machine and the Java Dynamic Application Component System (OSGI), it can work on many general-purpose operating systems, including Linux-based OSs for single-board computers such as Raspberry Pi and BeagleBone. For protocol stacks, Eclipse Cura supports some common messaging protocols, as well as the OPC UA and the Modbus, commonly used in industrial IoT applications. Let's look at how Eclipse Cura works. In this diagram, we can see that in order to use Cura on our target gateway platform, we need to have an operating system with the Java virtual machine and OSGI running. On top of it, Eclipse Cura defines services in different modules, including connectivity and the delivery module for messaging, data, and cloud services, network configuration module for configuring Wi-Fi, Ethernet, and the cellular modems, and the basic services together with remote management module and web interfaces. It also provides the API for accessing the hardware ports. In order to use Cura, we'll need to install the Cura on your target platform, such as Raspberry Pi or BeagleBone running Linux. Here I show you how to make the Cura work on our Linux host as an emulated gateway running Ubuntu. Here I'm using the Ubuntu with the VirtualBox on the Windows host. To run the emulated Cura, we'll need to install Eclipse with OOMF installer as instructed in the documentation. After the Eclipse is installed, we'll need to download the developer's workspace from the Cura's website. You can find that on the download page of the Cura website. Now, we can open Eclipse we just installed. Now, we need to import the developer's workspace we just downloaded into Eclipse. Here, we choose existing projects into workspace, and then select the archive file. Now we click Finish. Now there are several project packages imported, where now we'll open the target definition package at the bottom. And then we double-click the Cura Equinox target file. Now, we need to click this link, Set as Active Target Platform. Doing this will make the settings apply to other projects in the workspace. Now, let's open the emulator project. Now, let's open the emulator project and make it run. Now we click the OSGI framework in the menu. Since we're running Ubuntu, so we click the first option. Now the Cura emulator should be up and running in the OSGI runtime. We can check the web management interface by accessing the localhost and the port 8080 through our web browser. Then type admin in the username and password fields. Now we can see the emulated Cura services up and running through this web interface. The information services to all sorts of IoT applications. It's usually sitting at the top of an IoT system architecture beyond the edge. Many of today's commercial cloud computing services provide common services for IoT devices and their data. Let's see what the typical functionalities are. We can use cloud computing services for data storage collected over time from your IoT networks and perform some data analysis, as cloud computing endpoints usually have better compute power and larger storage than a single IoT device. Another common service is data visualization, where the data processed at the cloud endpoint can be rendered in any forms for view later. Some services provide web mashups, so that you can decide how your data is presented in, for example, a control panel with a switch to turn on or off the air conditioner by your sensor, a virtual gauge showing the speed of a motor, a chart showing the hourly temperature at your home on a day, or a digital number display showing the real-time temperature values. Some cloud services can allow users to define data logic of how to use the data collected. For example, we can define a role based on the temperature values transmitted from our temperature sensor to the cloud endpoint, saying if the current temperature value is greater than 86 degrees Fahrenheit or 30 degrees Celsius, then send a command to the home controller in order to turn on the air conditioner. Out of these services, the security policies and credentials can be defined, distributed, and manage it online throughout a cloud service. The security credentials such as keys, tokens, and access control policies can be managed and maintained on the cloud centrally. We can also do some device management functionalities by establishing an end-to-end connection between your application and the cloud service endpoint. As an example, let's see how to make a connection from our application to the multimodal Microsoft Azure Cosmos database for data storage and queries with the Python code in exercise file. First, we'll need to prepare a few things. Basically, we need to create a cloud data repo. So let's go to the Azure portal to create the Azure Cosmos DB account with sufficient Azure subscription permissions. Here, I'm just using the free trial Azure subscription. Once you log on to the Microsoft Azure portal, you can search for the Azure Cosmos DB services from the service bar on top. Let's click the Azure Cosmos DB in the drop-down list and click Add button to create a new Cosmos DB account if you don't have one. In this interface, you'll need to put the unique ID of your Cosmos DB account and choose database model. For this demo, I'm just choosing the Azure Table API. Then, you can create a new resource group and type its name. You can leave the other options and click Create button. In a few minutes, your Cosmos DB account should be created, where you can find that in the resource groups. Let's click the resource groups on the left sidebar. There are some resource groups I created before, so I just go ahead and click one. And this is the Cosmos DB account I created before. So click this Cosmos DB account you created, and you can check a couple of things here. First, you can click the Data Explorer menu on the left blade, where all tables and content entities can be quickly checked here. Make sure there are no entities in the table named the data table. This is because we'll create the table and entities with a sample Python code later. Also, you can check the Quick Start menu, where you can see some example codes showing how to programmatically connect to your Azure table. Now, let's click the Python tab and copy the line in the code starting with the connection stream. Now, we need to open the Python code in our exercise file folder and replace the same line with the one we just copied. Now, we have the data repo on the cloud and we have the right Python code, but also we need to make sure we have the Python installed on our computer. So you can install the Python following the instructions on Python's website. And also, we'll need to install the Python Package Manager, pip. So for instructions on how to install those two tools, you can check the README file in the exercise file folder. Now, assuming we have these tools installed already, and we have to use the pip to install the Azure Cosmos DB SDK for Python, we can execute this command at our command prompt. Since we have installed this module, so we're good to go. We can navigate to the Azure Cosmos DB example directory and execute the Python code here. After that, the data we saved to the cloud endpoint gets retrieved and displayed to the console. These data we saved to the cloud can also be checked through the Azure portal. If we click the Data Explorer of the Azure, such as provisioning, configurations, and updates on firmware, status, and diagnostic information. It provides added value to our IoT systems in general. From a user's perspective, updating software of our mobile devices and the smart gadgets from a trusted source or configuring devices remotely are typical examples of device management. Enabling device management capabilities requires the support from the IT system infrastructure and the IoT device itself. Since we have talked about the system-level setups and the standards in IoT Foundation's device management course, we'll focus on the device-level support, including the onboard OS-based applications. An IoT device being a device management client will interact with device management server, generally to take commands. execute DM operations, and send responses. A DM agent is the software that helps us do that, which can be part of your OS-based application. For example, the device-level support for remote provisioning and configuration would require the device to save data received from the remote servers to its own storage and do some possible encryption operations on the data. A more device-dependent functionality is software update. Software update, including firmware update, is a useful and common functionality, but we'll need to use the device software and hardware platform features to implement it. Let's look at the process of a software image update to see why. First, the software image needs to be downloaded from the trusted source, such as a secure remote DM server. Next, the image needs to be put in the storage device on board, which requires to be big enough to hold the image and preferably have a secure section for storing such image. Then, our application should be notified that the downloaded software image is properly stored and validated and is ready to go. At this point, the application will invoke API functions to initiate the over-the-air process, which requires the onboard firmware update support to do so. Our application should also check if the energy is enough to do such process. In case there's any issue occurs, the application should be notified by the OTA component and initiate a fail-safe procedure, such as a rollback, in order to restore the last state of the software image. If update process is okay, our application will be notified. Then we need to signal the remote DM server for reporting. There are two entities involved in the device firmware update. There are DFU controller and DFU target, where DFU target is the one the new firmware is updated to, and the DFU controller helps transfer the new firmware to the target. Now, we need to program the board with the NRF Go Studio, which can be downloaded from the Nordic Semiconductor's website. Then, we connected NRF51 DK board to our Windows host via the USB connection. At this point, our development board can be recognized by the tool, and we can see the memory structure of the chip NRF51422. Here, I just erase all the data in the target device memory to show the changes of the memory regions when we do the next steps. Now, we can program the software device into the NRF51422 chip memory. The software device is basically a Bluetooth protocol stack and is required for the over-the-air firmware update procedure for this device. To do this, let's click the Program Software Device tab on the right and select the hex file from the exercise directory for this chapter. You can select softwaredevice.hex. Then, we click the Program button to program the software device into the memory. Once that's done, you can see that the NRF Go Studio interface shows the region 0 of the chip memory is programmed with the software device. Next, we need to program the bootloader file into the device memory as well. So to do that, click the Program Bootloader tab and select the bootloader.hex file and click the Program. Now that we have all the firmware ready for the over-the-air update, but we need to make sure our Bluetooth board is in the DFU mode. To do this, we can hold the button for Onboard after power cycle the board. Now, the last step, update the application package through the Bluetooth link wirelessly from the DFU controller. Well, we definitely can use our computer to do this. We can use a computer with a Bluetooth adapter to do that, or we can use the mobile app called NRF Toolbox, available on Android and iOS mobile devices. This might be easier, as most today's mobile phones have Bluetooth modules built in. If you open this app, there is a DFU menu which allows us to select the application package, including the application file in hex format, signed by the private key to validate its source. You can just use the OTA_app.zip package we've prepared for you. Our DFU target board should be able to be discoverable by this app with the Bluetooth service called DFU Targ. I will leave this task to you. But once it's successfully done, the application running on the board can allow its It involves multiple levels, starting right from the single device, including hardware and the software is running, to the data transfers between devices across communication networks. In general, from operators or users' perspective, no matter if we have a large or small-scale IoT system, it's important to protect the device from being compromised and accessed by unauthorized users, to safeguard our device data, and to ensure only trusted apps are used. Depending on the roles of a device, every device may be set up with a bunch of different security goals. For example, in our smart home applications, we may not want our smart meters, smart lights, or garage doors to be controlled by the malicious users, or we may not want these devices get compromised by installing suspicious firmware images from unknown sources. If we use smart gadgets to monitor our health data, we want to keep the data confidential all the time, no matter if it's stored on a home computer or on a cloud. In an industrial setting, for utility or production automation systems, for example, any of these things happens will cause very bad consequences. There are quite a few technologies to help achieve different security goals of IoT devices that may be facilitated by some device management functionality. Let's walk through the device booting process to look at the generic device-level security technologies with the goal of making our IoT programs execute in a trusted environment. Suppose we have a smart meter using an OS-based program which is stored in a permanent storage. Assume the smart meter was just power cycled, and then it will initialize an OS bootloader, which is usually in the form of a separate small piece of firmware that helps load a general-purpose OS image to the memory. TPM is a technology used to initialize the hardware component and the secured OS bootloader, which can prevent a computer device from the malware infection, such as rootkit, which can hijack the device and conceal its OS image. Also, it can be used to protect the device-related data in some applications. After that, the OS bootloader is trusted to run in order to boot an actual OS image and then our executable programs. Then, we can say that the OS-based application running on this smart meter can execute in a trusted environment. Now, the device-level protection is in the hand of the application software. Sometimes, for small IoT devices, we may not use an OS bootloader, but just load the OS image right away after hardware initialization. This doesn't limit our use of a hardware-based TPM as a security chip. Establishing a trusted environment with a TPM is actually dependent on the processor platform we choose to use, as it usually requires the support from processor features. For example, if we choose to use ARM processors, we can use the so-called ARM Trustzone technology. It can use these ARM processors to facilitate the TPM features for small and generic IoT devices. For example, it can protect the ARM-based devices from unauthorized booting process or firmware updates. Within our application, including sensitive data or messages which may or may not be sent out through a network. These can add another layer of security to our application data. These can be achieved by using a symmetric key cipher such as Advanced Encryption Standard (AES), initially standardized by National Institute of Standards and Technology, or by using an asymmetric key cipher depending on the requirements of our application. Here, we're going to show how to encrypt your application data with AES cipher. More specifically, AES ECB cipher. There are quite a few embedded C or C++ libraries supporting the AES ciphers, and here we use the small library called Tiny AES 120A. This library supports the AES ECB mode and AES CBC mode, and it's included in NRF5 SDK version 12.3.0. Now, let's open the exercise file directory for this chapter, which contains a project folder for the target NRF DK board. Let's take a look at the source file, main.c. This file is based on the temperature sensor example used in Chapter 2, but we added another task function defined at line 116, because the AES ECP mode needs basically two parameters to encrypt the data. One is keystring and the other is the plain text. To this end, we defined a 16-byte key at line 119, and a sample 16-byte camel case Internet of Things string in the array at line 120. Then, the out array is defined to save the ciphertext. Now, at line 127, we invoke the API function in the AES library to run the AES ECB mode, where the ciphertext result will be saved to the out array, which can be printed to the serial port from line 130 to line 136. At line 129, we also simply toggle an LED indicator so that we can check if the program is running properly or not. Now we can compile the program and download it to our board. So to compile the program, we still need to copy the entire AES example directory into the SDK folder under examples. Now we go to the ARM GCC folder under the SDK directory to compile the program. If everything works well, we can copy the generated binary executable from this folder to the JLink drive. Now, we can also use the PuTTY to check the result. We can see that the AES encryption task runs around every 3 seconds as we defined, where the plain text Internet of Things and its ciphertext are displayed in hexadecimal for easy comparison. Since we know the AES key we used, we can easily decrypt it with the API as well. Note that the AES ECB mode we've just introduced here is simple to use and may be sufficient for some applications, but there are other AES modes we can use as well, such as the AES CBC mode, which is considered more secure than the AES ECB in many cases. Securing data transfers has been a demanding feature for modern IoT applications. A secure data transfer can happen between any IoT entities, such as between an IoT device and a remote server, at edge or cloud, or just between the IoT devices. If we are going to send any application data securely through the internet, we'll need an end-to-end secure logical connection for application data transfers. In this example, any messages from a sender will be encrypted in ciphertext without being eavesdropped or tampered by any attackers. The receiver will be able to decrypt the ciphertext later. This can be done through the transport layer security, which is responsible for securing the end-to-end logical connection. The fundamental technology of making that happen is the use of TLS. Using the TLS can also bring other security benefits in addition to the confidentiality brought to data transfers, such as data integrity. But let's see how the confidentiality is achieved through the TLS. One example use of TLS is HTTP over TLS, often referred as HTTPS. HTTPS is a preferred option for modern websites to secure the data exchanges between an HTTP client and the remote web server. If you see a lock sign on the address bar of your browser, that's the case of using HTTPS between your browser and the web server. How HTTP works is like this. Suppose our IoT device is a client and it wants to establish a secure end-to-end connection to another device as a server. Now, the server will send a certificate issued by an authority to the client. This certificate includes the server identity information and a public key. The client will then use this public key to encrypt stems from its autonomous learning and decision-making capabilities to react to the ambient environments and occurrences of events. This can be achieved by machine learning or, in general, artificial learning technologies. Machine learning is basically the practice of using algorithms to parse data, learn from the data, and apply the learning to make decisions or predictions about something. Deep learning, by this definition, can be viewed as a subset of machine learning. Machine learning has been used in many applications. For example, banks use it to predict the financial markets. Security software use it to detect the malicious attacks and the security risks. And cameras can use it to track human faces or actions. For smart home applications, we've seen the speech recognition capability on a central home controller, or on our personal assistants on mobile phones. Our voice command, "Please close all appliances at the kitchen," can be understood and recognized with the speech recognition engine. Intelligence on an IoT device can help solve many problems. For example, we can deploy multiple sensors to the field on a farm or in the garden to detect the best times for irrigation, or to facilitate crop management and harvesting in general. We can also use healthcare sensors and cameras at home to help elderly people to predict the health conditions and quickly respond to an emergency event. We can enable intelligence on a security camera surrounding our home to keep alert of the abnormal patterns of the videos or images taken by it. There are many applications we can imagine, but at a high level, to enable the intelligence on our IoT applications on devices, we can model the problem to solve first and implement that on the device, at edge or at the cloud. There's no simple answer to exactly where we should implement that, as it relates to many factors, such as hardware limits, power consumption, and performance, as well as user requirements. For example, if we enable an onboard intelligence capability requiring a lot of math processing, which finally consumes a lot of power we don't want, we may consider offloading that capability to the network edge or cloud. The fundamental implementations of intelligence on device is multifaceted and application-specific, but they all require the use of math processing capabilities. For our OS-based programs, we'll need to use an efficient math library that works well on our hardware platform. Although our microprocessor or microcontroller can do many math processing jobs, the performance can be improved with some hardware assistant computing. For example, a high-performance processor together with a math coprocessor, such as to make predictions of our data, or, in other words, giving insights into the data and making our IoT system smarter. A common task in machine learning is supervised learning, which can find out the functional relationship between the input and output of your data. Supervised learning can be applied to many IoT applications. For example, if we have collected two sets of machine data, one is for vibration, measured by accelerometer sensors, mounted on machines, and the other is for the states of machines. We may use it to predict the possible machine conditions in the future for maintenance purposes. In supervised learning, outputting such qualitative states is called classification. For healthcare applications, we may collect the health data from patients over time, and we predict the health parameters in the future for these patients. While these kind of applications still needs to be studied with scientific proofs. We can also use supervised learning for environmental monitoring, such as air quality monitoring, where, for example, we can use the atmospheric particulate matter 2.5 index dataset in the past and predict what air quality index will be in the future time. This is called regression, which can be done if a functional relationship can be explored by using a supervised learning algorithm. Let's take a look at how to use a typical algorithm for classification. There are several typical supervised learning algorithms for different problems, but we're not going through the mathematics here. Let's take a look at how to use a typical algorithm for classification called normal Bayes classifier. Programmatically, a common way to use such algorithm is using the math or machine learning library for your platform. Let's look at the popular OpenCV library, which contains the machine learning library with the normal Bayes classifier implementations. OpenCV has been broadly used in computer vision and machine learning applications. It has been released in packages for regular OS and cross-platform uses, such as Linux or Windows, Android, and iOS. Let's assume a hypothetical scenario here where we use the normal Bayes classifier to predict the states of a motor as shown here, where suppose we have a sensor board mounted properly on the housing of the motor, including an accelerometer, sensing the vibration amplitude data, and a temperature sensor, sensing the temperature at housing to indicate the bearing temperature. If we choose to run algorithm at an edge device, the radio board will be used to continuously transfer the sensing data to the edge. Let's assume that sensing data meets the conditions of using the normal Bayes classifier algorithm. Now, to use the algorithm, we need to give a training data first, and then train the classifier to get a model so that we can use the model to predict any input samples later on. In the table, we have a simple set of training data where each set of sensing data corresponds to a state of the machine, either in OK, warning, or error state. If we open the exercise 5 folder for this chapter, the sample projects for these scenarios that can be compiled to run on Windows and Mac OS or Linux are included. You can check the README file for more details. But let's see how to get it up and running with Visual Studio on Windows here. Let's open the Windows directory and open the sample classification solution file. Then we should be able to see the source file for this project. In this source file, we basically follow 3 steps of using the OpenCV normal base classifier API functions. First, we define an empty model. And then, we provide some sample training data in an array containing 9 sets of vibration and temperature data points, just as we saw in the table, as well as the labels for these datasets, which can indicate the states of the machine. After that's done, we can train the model. Once the model is trained, we can predict to see with the future sample data what the state of the machine could be. With a machine learning library on a single device. Now, let's talk about how to implement the machine learning algorithm with a cloud computing service, where in this case, the IoT can just consume the machine learning API hosted on the cloud computing endpoint from our vendor, and the heavy-duty compute is done at the cloud. At a high level, we'll need some software elements ready on different IoT entities. First, we need to have an API server endpoint running in the cloud, allowing the remote API calls from one or more IoT client devices. Second, our OS-based application needs to interact with a cloud API endpoint. If the APIs are provided through an HTTPS connection, we'll need to use the library supporting HTTP and TLS protocols. For other application-level protocols, such as CoAP, MQTT, and WebSocket, we may need extra protocol stacks, depending on the client or server role of our application. We have 2 basic options on enabling machine learning at cloud. We can use the generic virtual machine running Linux or Windows at cloud, write our own machine learning service program based on a machine learning library such as OpenCV, and deploy the program into an API endpoint, ready for being consumed with the secure access mechanisms. This option provides some flexibility, and it can also be applied to machine learning services and edge. Or we can use a machine learning solution from the cloud computing service vendor where some integrated tools are usually provided out of the box, so we can just focus on the problem to be solved. Here, let's take a look at the second option to see how to create a machine learning web service with the Azure Machine Learning to be consumed from your client OS application, where I'm just using the free tier Azure Machine Learning Studio account. First, let's log on to the Azure Machine Learning Studio portal. Here, let's start by creating an experiment with Azure Machine Learning Studio. Click the New and select the sample experiment in the gallery called Predictive Maintenance Step 3B of 3. Deploy web service with a binary classification model. This experiment is about the predictive maintenance scenario for equipment failure. The sample experiment uses a binary classification model to predict the probability that equipment fails within a future time period. It shows how to deploy the model into a web service that can be consumed by an application. If we deploy it into a web service, we can give some parameters for the piece of equipment, such as machine condition and failure history, and the web service will return a value to us, either 0 or 1, indicating if such equipment would be in normal or failure state in the future time. You can explore the details of this experiment, but here, let's see how to deploy it as a web service. To do that, we need to run the experiment and then deploy it into a web service. We can follow the on-screen instructions to do so. The running process may take some time, so once you submit it to run, you can leave it and check back later. If everything is okay, we should have published the trained model contained in this experiment into a web service. let's navigate to the web service from the left sidebar and click the web service name. And then, click the New Web Services Experience on top. Now, under the Quick Start tab, we can see the links for Test Endpoint and the Use Endpoint. We can quickly check to test the endpoint with some sample inputs for the predictive maintenance of the equipment. So the sample inputs are listed on the left column. Now, if we click the Test Request Response button, then the web service will give output values on the right column, including the scored labels 0, indicating with the input sample on the left column, the equipment is predicted to be in normal state. To know about how to consume the API endpoint, we can check the Consume for your OS-based applications. I hope they'll provide you a good foundation for building your IoT solutions. For the next steps, there are some chapters talking about IoT networking and device management topics. I encourage you to check out my other courses, such as IoT Foundations Low-Power Wireless Networking and IoT Foundations Device Management. You can build your IoT applications with the software libraries, tools, and their examples we've covered. And you can also check the documentation and support of these software libraries and tools.